And today we have talk of Kirill Kuchynskyi, devoted to asymptotic behavior solution to equation with interaction. So Kirill, please.
Okay, yes. Hello, everything. As it was mentioned, it's work devoted to stochastic differential equation with interaction, and it was written under the supervision of Andrei Anatolyevich Dragovtsev. Okay, and let's start. A lot of several times stochastic differential equations with interaction were mentioned during this year in this seminar. So I give a brief introduction what this actually is, and I mentioned some properties of it. And stochastic differential equation with interaction, it was introduced by Andrei Anatolyevich Dragovtsev in his paper of 2003, and it's stochastic differential equations, but the right-hand side contains term mu t, each of the coefficient, and mu t is the image of mu zero under the map X, and the whole idea is to investigate the distribution of interaction particles, how they move all together. And we have restrictions that the measure mu zero it has finite nth moment. Okay, and I already mentioned that there was several talks about such topics, so I decided to add some pictures to give an example. What is it? And for example, we consider some measure mu zero. It's somehow distributed on for example on R. And then under the change which governed by stochastic differential equation, this measure can shrink or extend in some case. And in this example, it's shrink. Yes, and actually the motivation and, for example, physical example where you can come and use such equations. We can, for example, see in the paper of Zirbel and Sinlar, they considered a little bit another problem is they consider the mass transported by Brownian fall in RD. And they provided example with pictures. For example, if we consider tracers, such as the quantity of crude oil that falls in the complex fluid flow, like ocean, and we want to understand the motion of the tracer in this example is oil, and predict how it changes. So this the whole theory has some background behind it. And I gave definition of stochastic differential equations with interaction in some abstract settings, but the main difference between stochastic differential equations with interaction and ordinary stochastic differential equation was in these coefficients. And we, for example, can consider explicitly how our point xut depends on the all other points. And for example, we can consider some function phi where xut minus v, and we integrate v over the whole measure mu t. Yes. And if it make a change of variables, we can see that our coefficient and our integrand, it's go over all other points in the space of RD. So our point xut has information about all other points, which is weighted by the measure mu zero. And it's like the whole idea about such equations that we know that single particle, no information about all other particles. And if we consider identity mapping, like simple one, then in this case, such coefficient is just our current point xut minus minus centroid or center of the mass at time t. Okay, and if I already mentioned this identity mapping, and now we can consider the example of stochastic differential equations of interaction which can be explicitly solved. And we consider the linear mapping. In this case, we introduced such some constant a, or in general cases, it's d by d matrix. And in such settings, we can actually try to solve this and solve. Yes, and in this case, we define the center of mass at time t. It's just the integral over all points x vt. And if we integrate a solution by over measure mu0 here, we can actually come to such.
Kyrylo, I have a question. So, do you average with respect to dv or mu dv?
One moment.
Mu0 dv.
Mu0 dv. Yes.
Thanks.
Yes. You and you here. Yes, and we get dm here. Yes, and in this case, this part is actually become 0, and we only left with d over linear process. Yes, and in this case, we can write explicit solution. Yes, and I should mention that in this case, in the center of mass, it moves like a Brownian motion. So the explicit solution is mu t, and all other points in which starts in the point u. We have that it deviate from our center mass by such coefficient. And again, I mentioned that our center of mass moves like a Brownian motion. So we can actually rewrite it that mu t and is the equal to bt. Yes, and to illustrate how the trajectory moves if we change the parameter r, I provided some illustrations, and I considered the simplest case when all one-dimensional, and if we take the r negative, this things strictly goes to 0, and these things it's vice versa goes to infinity, and the movement of the center, it's blue line. And in the case when a positive, all other trajectories they go out from our center, and in the case when a negative, it actually moves like a center of mass, and all points goes to and moves like a 1 point, and the whole measure mt is like only 1 point. And this example was illustrative in the sense that we want to understand how measure mu2 changes over time, and there is notion of this shift compactness that was introduced by Andrei Anatolyevich Dragovtsev in 2007, and we consider the set of measures. And in all previous cases, this A is just interval 0 infinity. It's our time, for example, or and we call it shift compact if measure shifted by some vector UA is compact set in the set of all measures. With such definition, it was actually we can there is a theorem by Karlikova, and she established the condition under which we can state that the set of mu-t is shift compact. And if we consider just mu-t and the random map satisfy a condition such that exists some constant greater than 0, and for any time t and for any points uv, our mathematical expectation of such norm is less than 0, less than equal than just difference between our initial points. And the main part about it that in the right-hand side of this inequality, we doesn't have t. And this is the criteria for shift compactness. And here we didn't mention the explicit form of our stochastic differential equation. We didn't apply any restrictions on coefficients, but from such theorem we can actually get conditions for if our x is governed by stochastic differential equations with interactions, and in this case, we need, in order to establish shift compactness, we need to add additional restrictions on our function phi and function b. And if we, in these settings, if we consider some measure mu0 with such a finite moment, and our function phi has such restriction that scalar product uv minus phi u minus phi v is less than or equal to this minus alpha u norm uv, and b satisfy Lipschitz condition, then such inequality holds true. This one, then in this case we can state that our set of measures is shift compact. And up to this time it was just like introduction what is stochastic differential equation, and some techniques how we can get information about the set of measures. And it turns out that if we hold this condition like this one, and this one for such stochastic differential equations, and we can actually get some new results about the existence of the limit in the infinity. And we consider the same stochastic differential equations with the same function phi and b, and we have the same criteria like for shift compactness. And in these settings, we can say about the existence of such limit. This prime phi is the I'll introduce this function a little bit later, but this is if we take okay, I introduce this a little bit later, this function, but from shift compactness, if we use criteria for shift compactness, we can actually say something about long-term limit of such difference. And it's actually the main result of my paper, and then the next part of the talk is dedicated to proving such results. And before prove it in in RD, because here we consider the dimensional case. Before it, there is work of Logunova of 2012, and she considers the most simple example without the drift, just as a diffusion term, and she managed actually to establish the limit of such difference that it's actually exists almost everywhere for any point u and v. And idea of her proof is if we consider such a difference, this difference is non-negative martingale, and we can represent it using random change time, and this is this time, and because this things on left hand side is greater than 0, we actually need that, or the right hand side is also will be greater than 0. And in order to do it, and on the right hand side we have Brownian motion, and Brownian motions in one-dimensional case is point recurrent, and then the whole random time this is actually is less than tau uv, and tau uv is defined by the first Keating time of minus u minus v, because it's the first time it hits 0, and it can go to and the whole left hand side difference can be less than 0, but our restriction is that it's actually greater than 0. And because we know that these things don't go to infinity, and we can establish the existence of such limit. And this was done in one-dimensional case. In d-dimensional case and in general settings that we also have a diffusion term and drift term, and in order to establish it in this case, we actually can use this similar approach, but add a little bit machinery to it. And again, it's just a repetition of the main statement that if we have such restrictions, then we can apply the existence of such a limit. And about the function f prime. Yes, it's actually if we using eta formula for such norm, and we have 3 terms, and again we have such drift term and diffusion term, and this is drift term. It's what we used in the statement of the main theorem. So if we take such norm minus drift term in decomposition, then we can establish existence of the limit. And actually here the proof, it's we start with such representation. First we start with for example with diffusion term. We have d diffusion terms. It's we consider separate separate function ik. They are because they are mutually independent, because our Brownian motion independent. We have that their quadratic variance is equal actually to the sum of such integrals. And again, we can use the same trick that Logunova used, and that we can represent such sum as time change Brownian motion. And in this case, we managed to represent this term as a random time change Brownian motion. And now we in order to use the previous approach, we can actually again try to get the non-negativity of such things. And in this case, if we achieve this, we can again state that the Brownian motion is point recurrent, and the whole time how it moves is actually restricted by some random time. And again, we can state the existence of limit, and how we actually can get that such difference is non-negative. We can represent phi, and we can actually explicitly calculate phi, but because it's two-dimensional, it will be a lot of calculations. These calculations are presented in my paper, but in presentation I didn't include it because it looks a little bit scary. But the whole thing, if we use a restriction on function phi, that you and then we can get such inequality. And the third requirements in the proof is that this thing is less than zero. So this term is also less than zero, non greater than zero. And in such case, we know that this whole thing is non-positive, and then in this case, such norm minus this drift term is greater than zero. And now we can actually a little bit enhance this inequality and achieve strict sign, and because such integral is strictly greater than zero, because our point starts from u minus v, and they are continuous, and so the whole integral is greater than zero. And in this case, this difference is also greater than zero. So we have our initial difference. We used iter formula to represent such function in with the drift and diffusion term, and we substitute drift term. And in the right hand side, we get representation or right hand side with time change Brownian motion. And we know that this is the whole thing is greater than zero, and this is Brownian motion. So we again can restrict this random time with some t uv, and tau uv, and tau uv is the time of first heating of such difference. And we again can say this then the whole limit exists because this time is restricted, and Brownian motion is a point recurrent. And this is the proof, the final step in the proof of the theorem. And also using the similar idea, we can consider a little bit a different norm. And previously we considered just such norm, but now we can consider we can integrate it over du and dv in this case. And these things which we call internal energy, and I find such things when I read about local times, but I think it can be used in many cases, but using such epsilon t, we can actually again state about the existence of such difference. And to prove it, I didn't provide any detailed proof how to manage it, because it's actually pretty similar to what I did previously. We just have some integration over measure mu0 du dv. And we again can state that long-term about the long-term behavior of such epsilon t. Yes, and this function phi is a representation using Ito formula for such thing. And using the same argument, we can conclude that the left-hand side, if we move these things here minus, and on the right-hand side, we have such diffusion term, and we can again use this representation with time change Brownian motion. So, and the final statement of the theorem is can be deduced from it. Yes. And these papers that I mentioned earlier, and I think that's all. And yes, you can ask questions.
Okay, thank you for such presentation. Maybe somebody have questions or comments, please.
I have a question. Why the limit is positive? It may be 0, I think.
Why the limit is positive? Vic, 1 moment. Because these things is strictly greater than 0. Because yes, we have conditions that u doesn't equal v.
Yes, for fixed u and v and finite t, this random variable is not.
Yes.
0. But a limit may be, who knows? The limit of positive numbers may be 0.
But we consider the integral, it's how can
I see, yes. It is not averaging. Thanks.
Okay, maybe.
Okay, some other questions, please.
No. I have a question. So integral is positive, but when you consider this difference, positive minus positive, the limit may be 0, I think. For example, let us consider your first example where interaction is with matrix.
Interaction with matrix. Yes. This one?
Yes. If all eigenvalues of A are negative, then probably xut converges to m of t, almost surely.
Yes.
And maybe if you subtract, your integrals will get 0 in limit, I don't know.
Of course. Of course. So maybe some other questions, please. Okay, if there are no questions, so we shortly finished our work today. And Georgi, who will be the next speaker?
The next speaker will be Nasir Gadbeni-Hadjaev.
Oh, very good. So for today, that's all. Thanks, everybody, and bye.
Thanks
Okay,
for the
bye.
good talk and for pictures.
Bye.
They were helpful.
Bye.
Bye. Yana,
Bye.
nice to meet you.
Yeah.
Okay, bye.
Bye.